Hello students, welcome to E-PG Pathshala. I am Dr. Dinesh Kalyansundaram from IIT Delhi. Today we are going to talk on a module on ordinary differential equations. What is a differential equation? That is what we are going to see, and how is it different? Where is the need for a differential equation? What are the types of differential equation? And how are we going to solve the differential equation? This is what we are going to see. Differential equations are indispensable part in a real life situation. When in every phenomena something is changing, and that is what we are going to see how to model it when something is changing. Why can't we use analytical equations? The problem is, in a differential equations there is a variable, a change. For example, a jug where the shape of the jug is not straight. If it is straight, we can have a simple equation. When it is curved and it follows a certain pattern which is not linear, then we might need to use a differential equation. Differential equation always contain a derivative terms, and that's why it's called a differential equation. One or more differential equations can represent a complete system or a complex system. Differential equation is very useful for any mathematical modeling. So every mathematical modeling or any mathematical modeling has differential equation as a part of its modeling process. We want to understand why do we need differential equations. So if the need is properly understood, then we can learn the subject more thoroughly. Imagine you have a jug as shown in the figure where the radius is continuously changing, and imagine there is a hole in the bottom and the water is leaking out, and you want to find the volume of water as a function of time. That means at different times you want to know how much water is left behind. So how do we do that? Now one way is to do it manually, conduct an experiment at different times and write a chart and do that. But that's a very tedious way. How can we do it in a more simpler way? The more simpler way is to write a one-line equation and then put in some values, what we know, and then find out what we don't know. Now what we know is volume of the water, and what we know is the volume is continuously changing with time. So we know behavioral pattern. So our requirement is to find some relationship between how much volume is left behind to how much volume is. So we can form a differential equation. This is one of the forms, and then you can find out different forms. dH by dt is minus AH by AW root of 2GH. So these kind of equations can help us in one line find out what is the height of water remaining or the volume of water remaining. Some parameter that we don't know, we can always find. Let us see a second example to understand the need for a differential equation. As most of you are from a bio background, and most of you or some of you may have experience in growing cells, and we want to understand how the rate of growth of cells is as per unit time. Now you also know it is not always proportional or it is not exponential. There is some relationship, but from experience you might have found out maybe a certain time, maybe a day for E. coli, or maybe 3 days for Salmonella typhi is better, or it may be different timelines. Now how can we find out in a more rigid and a scientific way? So to understand that, we can derive or describe an equation based on the empirical experimental stuff, and you can write your equation. For example, dy by dt, which is the rate of increase, is k times y into m minus y. So these kind of equations will describe what are those later, what are those parameters. But when we want to do computer programming or anything, we want to define everything in terms of equations, which is easier to solve rather than give a complete data sheet and then pick and match values. It is more complicated.
What is the need for a differential equation? Because there is a difference between what we are seeing and what we actually want to measure or want to know. For example, we may see a particle is moving or it's stationary, or there is a change how it is undergoing in terms of displacement. But what are we interested to actually understand? We want to understand how fast it is going, or what is the velocity, what is the acceleration. We want to know the displacement. If the same body gets crushed, the particle gets crushed or the body gets crushed, we want to know how much deformation it has undergone. Or sometimes we want to know both the displacement and deformation. Or deformation is the change in the shape, displacement is the movement from one point to another. We may see an object which is just hot or cold. We know there's fumes coming out, but what we may be actually interested in, we may be actually interested in knowing its temperature, knowing whether it is going to melt, knowing whether it is going to crack. That is what we need to know, and for that we will need temperature. But what we will see is only steam coming out of an object. We may see a geometry of an object is changing or not. But what we may want to actually know, we may want to know the quantity, we may need to know the deformation. We may see there is a growth or a decay of a material. But what we really want to know, we want to know the rate of growth or rate of decay. We may see some energy has to be applied to do some work. We may see a bulb glowing, we may see some machines working, but actually how much, what do you want to know? We want to know how much voltage the machine is drawing or how much power the machine is drawing, and we also want to know how much force the machine is going to apply drawing a certain power. So these are some things that there is a difference between what we look, what is happening, and what we exactly in the information what we want. So to connect these two is when we will need a differential equation.
We want to understand the effect of boundary value. Now, let us assume there is a differential equation d squared y by dx squared minus 4y is equal to 0. Now, why do we define a system just by one differential equation? Can it really replicate a real system? Now, let us assume that the solution of the equation is y is equal to c1 times e to the power 2x plus c2 times e to the power minus 2x. Now, how is this going to understand or capture or help you follow different systems? So, the solution of a differential equation or the differential equation itself is only half of the problem, which means it can only give general information. It can never identify a system. What helps you identify a system? The key component is a boundary value. Without this, no equation can predict a system. So, let us see for initial values or boundary values. Boundary values can be in terms of time or in terms of space, which means at the edges how it is or at the center how it is and all this. So, let us assume an initial value y of 0 is equal to 4 and y dash of 0 is equal to 1. If you substitute these values, right, then you can find the value of the constants c1 and c2. So, once you find the constant values, now you can substitute them. Now, the general equation or the solution is going to be y is equal to 2.25 e power 2x plus 1.75 e power minus 2x. Similarly, for different boundary conditions, you can see the solution is getting different. Now, how does it matter? All the equations look nearly the same. So now let us go into the next slide to understand how it is really a different phenomenon. As we saw earlier, we had different solutions depending on the boundary conditions. We are going to see graphically how it is different. Now, as you can see in the slide, you are seeing a red curve which is in the form of a U, and this is a solution for the initial condition of y of 0 is equal to 4 and y dash of 0 is equal to 1. Now, what is the speciality of this? Like you can see, the solution is closed, it forms a closed end in one side and it's open on the other, which means the solutions can only be in the positive regime. So this will have a different effect problem. Let us go to next slide to understand the different boundary conditions. We are going to see how the second type of solution for the same differential equation is going to really change the solution type. Now we are looking for the boundary condition y of 0 is equal to 0 and y dash of 0 is equal to 1. Now you can see the violet curve is in the shape of an S, an inverted S or a rotated S. Now you can see that the solution is open on both sides, which means the values of y changes, but in the x-axis it is more restricted. So the values of x it can take, it's actually restricted. So it is not existing for other x values like 4 or 10, it doesn't exist. Now we are capturing a different mode of the same phenomena. We are going to see the third solution for the same differential equation. Now here the boundary values are y of 0 is equal to 0.5 and y dash of 0 is equal to 1. And here you can see the curve, blue color curve, is completely different than the previous two curves. I can't say completely different, but partially it is different. So one side it has a u and the other side it has a value 0 all throughout. What we saw in the last few slides, I just put them together in a single slide. As you can see, y1, y2, y3 are all different forms of this of solution for different boundary values, and that is all happening for the same differential equation. So differential equation captures only one part of any problem, but it is the boundary values which actually define the exact behavior of the solution. Conclusion is the differential equation has power to solve different boundary value problems when you compare it to an ordinary equation. Let us see some few examples of classification of differential equations. What are the classifications? Classifications actually happen when each differential equation will capture different physics, and once we have different physics, then the boundary, with the help of boundary condition, then we can come to the exact solution. So the first step is to correlate the physics with the differential equation. So that's what we are going to see in the column 1 and column 2. Then we will see what is that we really wanted to understand from that by solving that equation. What is the first physics of the problem we want to see? Cooling of an object. So any cooling type of problems can be solved with this equation. D capital T by small dt. The capital T refers to temperature and small t refers to time, and these are standard notations, so please follow the same, is equal to minus k times T minus TA. TA is going to be the T ambient, the room temperature, and it's always better that you always write T in terms of Kelvin. Now the desired solution here is they want to understand the temperature of the object. That means T ambient is known, the K factor is known, K is a proportionality constant. We can see once we are solving a heat equation, what really K refers to. The second example is pushing or pulling a mass or an object. So the differential equation related to that is the force required is again a proportionality constant, here m, then d squared x by dt squared. Now dx is the displacement and dt is the time during which the displacement happened. So what we are interested in is to find out what is the displacement of mass given a force. Growth of cells is a third example. Like we saw, we are seeing dy by dt is equal to k times y m minus y. What are we interested? We are interested in the growth rate m, total number of cells. Fourth example is consumption of goods or product. Dy by dt is equal to minus k times y. Then what we are interested in, we want to understand how much goods are getting used up. So, or the shortage, how the goods are changing. Now you can see whenever there is an increase in something, then we use a plus sign on the right side of the equation. Whenever there is going to be a decrease, we are using a minus sign. So growth of cells is going to grow, so we are using a plus sign. The force will always cause a increase in displacement, so we are using a plus sign. A cooling of an object, you are going to reduce the temperature, so we are using a minus sign. And the shortage is again going to be a minus sign.
What is differential equation? A differential equation is an equation involving derivatives of an unknown function. Remember, unknown function, and possibly the function itself as well as the independent variable, or a relation between two or more physical quantity when the rate of change of one quantity or derivative with respect to other will be present. For example, dy by dx is the rate of change of y with respect to x. Okay, so dy by dx plus 2y minus 7 is equal to x. So this is a differential equation. Or d squared x by dt squared plus 8 dx by dt plus 3x minus 7 is equal to t minus 1. This is also a differential equation. So we can actually have different forms, and we are going to talk about them later in the course, in detail. Now first we have to, you might have heard about two different types of differential equation, like ordinary differential equation and partial differential equation. What is the difference? It is very important to know the difference at this point. The difference I am going to tell you. In an ordinary differential equation, we are going to have only one independent variable. That means there is going to be only one x which is in the denominator, and there can be many variables which can be y, z, alpha, beta, anything. So a equation like y dy by dx is equal to sin x is an ordinary differential equation. And or something like y dy by dx plus dz by dx is equal to sin squared 2x. This is again an ordinary differential equation. There are many variables, but they are all dependent on only one independent variable, that the source is only one, where the change is going to be referenced. If the reference is only one, then it is ordinary differential equation. When the reference can be more than two, for example, you change as with respect to space, like x, y, z, and you change with respect to time. Now there are four different variables that you can change with respect to. So if you are doing that, then it becomes partial differential equation. For example, in partial differential equation, we use dou instead of d. It's just a mirror image of d, but then we just write with dou. Dou u by dou x plus dou u by dou y is equal to 3. That's a partial differential equation.
We want to understand order and degree. The order of a differential equation is equal to the order of the highest derivative that it contains. So let us see the example. Now we have d cube y by dx x cube minus dy by dx whole squared plus 4y is equal to 4 e to the power of x cos x. Now the order of this equation is the term that will define the denominator. So you can see the denominator. Which of the x's is differentiated more number of times? So the first term is dx cube. The second term is going to be dx whole squared. So inside the square it's just a multiple, but the differentiation is the x is in the second term, the x is only differentiated once. But in the previous term, that is the first term, we are differentiating with respect to x thrice. So the order of the differential equation, that is the highest derivative. So the highest derivative order is 3 here. So that's why it's a third order ordinary differential equations, ODE. Now degree, once you fix the order, then the degree is going to be degree of the of that particular term. Okay, so let us see the proper definition. The degree of a differential equation is the highest power of the highest derivative that the equation contains after it has been rationalized. So we have located what is the highest derivative. Highest derivative in the first equation is dx cube, that is the highest derivative term. Now what is the highest power? Power meaning what is that factor, how many times it is getting multiplied. Now once we do third order differential equation, we are not multiplying several times, like say the second term, you are seeing dy by dx is getting multiplied twice, right? So it's dy by dx squared, but this d cube y by dx cube is not multiplied any number of times, it's multiplied just once with itself. So it's a first order, first degree ordinary differential equation. So let us see a second example in the bottom. Now you see a first term d squared x by dx of t, basically x is a function of t, by dt squared, and it is multiplied 3 times. So when you compare all the equation, dt squared in the bottom will tell you what is the order of the equation. So the order is going to be obviously 2. Now once we located the term, the highest term is 2. Now we are going to locate how many times the same term is getting multiplied, and it has a function 3 cube. It is multiplied 3 times. So it's a third degree ordinary differential equation. Next thing we want to understand is whether it's a linear or a non-linear differential equation. Differential equations are said to be non-linear if any products exist between the dependent variable and its derivatives or between the derivatives themselves. Let us see the first example. The first example, so you are having different terms, d squared x, then by dt squared, then second term is dx by dt, but it is not having a square. That means the degree is not there. The degree is nearly 1 and the order is 2, right? So this is a linear differential equation. In the second term, we are going to see that it is having dy by dx term as shown in the square red box, and it is getting multiplied twice. But all other terms on the numerator, y, they are all single terms. But the second term is getting multiplied twice. So that creates a product term, and that will ensure it's a non-linear behavior. And let us see the third example to understand this next level. You can see y squared is also marked. That is, it's a product between the dependent variables themselves. However, this is also considered as a non-linear. So it doesn't matter whether it's a dy term which is getting multiplied, or whether it's a y term or the dependent variable which is getting multiplied. both will have the same non-linear effect.
Some methods to solve differential equation. First order differential equation. No general method of solution of first order ordinary differential equation because of their degrees of complexity. Okay, they can be classified into equations in which the variables can be separated. There can be homogeneous equations, then equations solvable by integrating factor.
We are going to see how we are going to solve differential equations to obtain the solution. The easiest or the most simplest form of differential equation is what we are seeing now. The dependent variable and the differential can be separated from the dependent variable and its differential by the equality sign just by a normal process of elementary algebra. Y dy by dx is equal to sin x. That is one example. Then the solved example, you can just see similarly, dy by dx is equal to x by y. Then you can take y dy is equal to x dx. Then you can integrate separately on both sides. Then you will get y squared is equal to x squared plus c. Similarly, you can solve the example y dy by dx is equal to sin x, right? So it will become y dy is equal to sin x dx. Then you can integrate both and you can get the solution. The previous example where we separated the equations, variables dy by dx is equal to x by y, we integrated and solved it separately, y squared is equal to x squared plus c. Now depending on the c, the curve is going to change again, right? That's what we earlier saw. That time we were seeing depending on the initial value condition. Now we are seeing the initial value will affect the value c, and this is how it is going to change the pattern. As you can see, we are having a lot of solutions, and at one special case where c is equal to 0, y is equal to x and y is equal to minus x are the solutions. And then you can see a sharp corner. We want to see, understand what is a homogeneous equation. A differential equation of the type dy by dx is equal to some function of y and x, but there is no constant. If there is no constant and it's only a function of f and y, then it is called homogeneous equation. Such a equation can be solved by either making a substitution y and x in a different terms. So here we have assumed y by x is equal to u, and it may have different functions also, y into x or different things. Then you can therefore integrate. So now the whole equation will be written in terms of u. But the key thing that we have to understand is that when there is no constant term we are going to integrate, then it's called a homogeneous equation. So here we are going to solve the equation using an integrating factor. Assume there is a differential equation in the form dy by dx plus py is equal to q, and where p and q are functions of x only. That means it can have different coefficients and stuff. Then you can always assume r is a function of x only, and you can have a factor like r is equal to e power integral p dx, and this you can use it as an integrating factor. Now we will see more examples to understand how the integrating factor going to work. We are going to see one example to solve the equation using integrating factor. Now assume we have a differential equation to solve xy minus dy by dx is equal to y to the power 4 e to the power minus 3 x squared by 2. Now we want to solve this equation using an integrating factor. Now let us assume z is equal to 1 over y3. It's just an assumption. We can assume different forms. Then we can see how it is going to really affect. So if we use z is equal to 1 over y3, dz is equal to minus 3 by y to the power 4. Now why do we do that? So that when you multiply the right hand side, y to the power 4 will get cancelled. So that is the whole idea how we started with this initial guess of what y can be. Now dz by dy is minus 3 divided by y power 4, but then we have to also find out what is dz with respect to dx. So here x is the independent, y is the first stage dependent variable, and z is the second stage dependent variable, because z depends on y and y depends on x. Okay. Then so that we have to now do z with respect to x also. Dz by dx will become minus 3 by y power 4 into dy by dx. So that's the thing we are going to do. Now let us substitute that into this equation. So we are going to place y completely out, and then we are going to write only x and dz. Now that is what you see in the first equation on the right hand side. 3xz plus dz by dx equal to 3 e power times minus 3 x squared by 2. Now let us choose the integrating factor, which is e power integral 3x dx. Now that will give rise to the integral factor e to the power 3x squared by 2. Now let us multiply that e to the power 3x squared by 2 in all with all parts of the equation, right? So left side we will multiply and right side we will multiply. So if you see, if you multiply on the right side, it just becomes 1, because the minus and plus in the e gets cancelled and it gives rise to 1. In the left hand side, we can actually write the whole term now as d by dx of z e to the power 3x squared by 2, as shown in the equation in the last of the first on the right hand side in the right corner. Now once you have in a d by dx form, you can always integrate it. Then you can always write z e to the power 3x squared by 2 is equal to 3x plus c. Now what is the solution? Now you have to convert from z, replace z in terms of y. So if you replace that, now you have the exact solution. 1 by y power 3 e to the power your integral factor is equal to 3x plus c. Now that is the solution. If we want to solve the same equation otherwise, it will be more difficult than this part.
Ordinary differential equations. Linear second order ordinary differential equations may have coefficients. Either the coefficients like PQR and psi are PQR are constant, or they can be functions of the independent variable. What is independent variable? X is an independent variable that we were actually seeing. So they can be functions of the independent variable. The general equations can be expressed in the form where PQR are constant coefficients.
We are going to see how we can write a solution y of any equation. We can always write any equation as part of more than one quantity. So we can just say u, v, w, z stuff. But the more practical way is to have two equations. One is called a general solution and the other is called a particular solution. The general solution is thought of equating for an ideal condition. The particular solution will take care of the effect of other variables. Okay, for example, we talked about homogeneous and non-homogeneous function. What is a homogeneous function? There is no function on the right side. So dy by dx plus f times whatever function x is or y is was equal to 0. So there was no effect of other equations considered. So similarly, we can write two equations separating y into u and v. So if you have any equations p plus d squared u by dx squared plus q du by dx plus ru plus the v term. Now actually the equation was p p d squared y by dx squared plus q dy by dx plus ry is equal to some function psi of x. Now we are writing it into 2 in terms of u and in terms of v. We are going to assume that u is the general solution, which means we will equate it to 0, which is the ideal condition, where the function has no other connections to other forcing functions or other terms. And then we will solve v separately, where v is the only responsible for the psi of x. So now we have two parts of the equation, and we are going to solve one at a time. We are going to see the complementary function of the equation, how we can solve this. We have the equation p d squared y by dx squared plus q dy by dx plus ry is equal to 0. Let us assume the solution y is equal to a constant times e to the power mx. Generally, equations of this will have this type of solution. So we can write dy by dx is equal to am into m into e power mx. Similarly, d squared y you can differentiate and find out. Now, if you write the whole p d squared y, the first equation, in terms of am and e power mx, then you can see am e power mx will become the common term, and then pm squared plus qm plus r will be the equation we need to solve. So when we have this equation, either it can have unequal real roots or equal real roots or complex roots.
We are going to talk about particular integrals. Particular integrals is when we are going to equate the solution to the right hand side psi of x. Then we need to find the particular integral. Two methods will be introduced to obtain the particular integral of the second order or linear ordinary differential equations. It's not second order, but just the ordinary differential equation. First is the method of undetermined coefficients. This is confined to linear equations with constant coefficients. The second method is the method of inverse operators, and it's applicable, it has general applicability.
We are going to find the roots of any equation. So for the given equation as shown, d squared y by dx squared minus 5 dy by dx plus 6y is equal to 0. You can write any y d squared as m squared, then dy as m, and y it's not differential, you can just write just the number 6. We know the equation, the roots of this equation is m1 is equal to 2 and m2 is equal to 3. The solution of such differential equations is going to be a very simple one. Y is equal to a to the power a into e to the power 2x plus b into e to the power 3x. Now how do we find a and b? That is with respect to the boundary values x. At this x is equal to, they might have given some values 1, 2 or 5. Then another y x value means there will be another number. So then when you substitute, then you can find the actual constants a and b. Since we have two constants, we will need two conditions to actually come to the full equation. Let us see the roots of the auxiliary equation for a condition when the roots are equal. That is, m1 is equal to m2 is equal to m. And let us see how the solution is going to change. So therefore, let us say y is equal to v times e power mx. Then dy by dx is equal to e to the power of mx dv by mx plus m times v into e power mx. That is, we differentiate v first, then we differentiate e to the power of mx second. Similarly, d squared y will give you some terms. Now, if you put v as a function of x and then put it into the general equation p d squared y by dx squared plus q times dy by dx plus ry is equal to 0, we can end up with d squared v by dx squared is equal to 0, which gives the solution v is equal to cx plus d. Therefore, the solution is going to be y is equal to cx plus d times e to the power of mx. We are going to see how the equal roots to the auxiliary equation with an example. So let us assume d squared y by dx squared plus 6 dy by dx plus 9y is equal to 0. So if we write in terms of the auxiliary function, it is m squared plus 6m plus 9 is equal to 0, which ends up giving us both roots as equal to minus 3. So the solution has to be written in terms of y is equal to a plus bx into e power minus 3x. We are going to see unequal roots to our auxiliary equation, but this time the unequal roots are complex in nature. For the equation d squared y by dx squared minus 4 dy by dx plus 5y is equal to 0, we have the solution m is equal to 2 plus or minus I. So if you the actual way is if you write, then you will get y is equal to a into e power 2 plus I times x, then b e to the power 2 minus I times x, and so the general equation is going to be e to the power of 2x capital E cos x plus f sin x.
Now we are going to see how we can operate, use the D operator on ordinary differential equations. You can treat these D operators as similar as any algebraic quantity. D times B plus C is equal to dB plus D times C. So it doesn't matter. The commutative law, A times B is equal to B times A, but you have to be very careful. Now it does not mean d of xy, let us assume there is a d operating on xy, that is not equal to x times d into y. So x times d into y will become, you are multiplying x after differentiating y with respect to d. So that's not right. So you will have to see where the operand is, then you have to actually see how it is getting operated. So it's always good to write the brackets so that we know where and how it is getting operated upon. Then the associative law, where AB first multiplied into C can be written as A times multiplied with the product of BC. So D times of dy, okay, can always be written d into d of then y. Okay, so that's what it means.
Going to solve about a method of undetermined coefficients. Then we have the general equation p d squared y by dx squared plus q dy by dx plus ry is equal to psi of x. When psi of x is constant, say c, then the particular integral equation will be equal to y times y is equal to c by r. When psi of x is a polynomial of the form a plus a1x plus b2x and kept on going, where all the coefficients are constants, that means a0, a1, a2 are all constants, then the form of the particular integral is going to be y is equal to alpha naught alpha 1x alpha 2x squared, then up to alpha n to the power xn. Remember, the coefficient will the solution also will have to be up to the same x power times n. When psi of x is of the form t into e power rx, when t and r are constants, then the particular integral will again be of the form y is equal to alpha times e to the power rx. When psi of x, now the psi of x is what we call it as the forcing function in some places, and psi of x is 0, then it's we do the auxiliary equation. When psi of x is not a constant, is not 0, and that is when we are having these all the four conditions. The fourth condition is when psi of x is of the form g times sin x plus h times cos nx, g and h are constants, then the particular solution is particular integral is going to be of the form L times sin x plus m times cos nx. Before all these slides, we saw very confusing forms of how to deal with differential equations. So now we are going to conclude. So maybe this time it will make more sense how we are going to actually solve a completely complicated differential equation. You see the equation in the left top corner, d squared y by dx squared minus 4 dy by dx plus 4y is equal to 4x plus 8x cubed. Now when we want to find the auxiliary equation, we go right side. Then we write m squared minus 4m plus 4m plus 4 is equal to 0. So then we are going to solve that directly. If you know in this the roots are going to be same, so it is going to be a plus bx times e to the power 2x, because the root is equal to m is equal to 2. Now we will go and solve the particular integral. For the particular integral, since the constants on the right hand side of the equation 4x plus 8x cube, so as we saw earlier, we have to write it in terms of another polynomial which will go up to x cube, right? So y is equal to p plus qx plus rx squared plus sx cube. That is our initial guess of the solution. Then we are going to find out what is the value of p, q, r and s. Now dy by dx is going to be q times 2x 2rx plus 3 times sx squared. Then d squared y is equal to going to be 2r plus 6sx. Now you have to substitute in the complete equation in the top. Now you are going to get in the form of in the middle equation. Then we have to go into equate the powers on both the left and the right side. Okay, that is how we are going to find the value of p and r and q and s. So we are going to get 4 equations because we are going to equate it to the powers on the left and the right side. You can see 2 of the equations will be equated to 0 because there is no x squared and there is no constant term. So that will be equated to 0. And there is x term and there is x cube term, that will be equated to 1 and 3. So sorry, the constants 4 and 8. So when you solve it, you can find the particular integral 7 plus 10x plus 6x squared plus 2x cube. Now what is going to be the complete solution? Complete solution is going to be complementary function plus particular integral. Method of inverse operators. Sometimes it is convenient to refer to the symbol d as a differential operator instead of writing the complete term dy by dx. Okay. So what we are going to say, as you see in the bottom of the slide, d squared y by dx squared plus 3 dy by dx plus 2y can be easily written as d squared y, capital D squared y plus 3 dy plus 2y. Then you can find, you can even write it more simple form as d plus 1 into d plus 2 times y.
Unequal roots to the auxiliary equation. Let us say we solve the equation, there are 2 different roots. So, and these 2 roots are not equal, then the solution is going to be, first solution is y is equal to a1 e power m1x, and the second solution is going to be a2 times, which is another constant, into e to the power m2x. Okay. So what we are going to say is, any general solution for that such a problem is going to be sum of the solutions. Okay, so it is always mathematically a procedure to say that any complicated problem, when it has more than one solution, we write it as a sum of solutions. That means either of them can be the solution of the problem, right? So y in total is equal to a1 times e to the power mx1 plus a2 times e to the power of mx2.
We are going to see how to put differential operator for exponentials. So d to the power into e px can be written as p times e power px. Then d power n is equal to just going to become p power n times e power px into e power px. So any equation d squared plus 3d plus 2 as shown on the right hand side corner, top corner, into e power px can always written by as p squared plus 3p plus 2 times e power x. We are going to see how to put differential operator for trigonometric functions. So d to the power n times sine px is equal to d to the power n imaginary number into e power ipx. So im represents the imaginary part of the function, which follows as given in the lower box. E power ipx is cos px plus I sin px. So then you can actually see how d to the power 2n, how d to the power squared, everything is going to change. we are going to see how to perform the inverse operator. The operator d signifies differentiation. So d integral f of x dx is equal to f of x. So the integration and the differentiation gets cancelled out. Now you take the d on the to the right hand side. So integral f of x dx will be written as d inverse into f of x. So d inverse is the inverse operator or the integrating operator. It can be treated as algebraically the same quantity in the same manner as d. We are going to see a complete example how to use the inverse operator. You know the whole differential equation can be written as auxiliary and particular function. Auxiliary, when we write, that is on the right hand side, which is m squared minus m minus 6 is equal to 0. Then the solution complementary is going to be yc is equal to a into e power 3x plus b into e power minus 2x. Now we will see how to use find the particular integral. Particular integral, then we have to write d squared y by dx squared as capital D squared. Then once you write that form, then you will end up having yp is equal to 1 over d minus 3 into d plus 2 totally multiplied to 4x cube plus 3x squared. You can separate the variables, do some algebraic things, and then you can write it as 1 over 3 minus d plus 1 over 2 plus d. Then you can expand them each term with a binomial theorem. Then you can end the day find out yp is equal to this whole equation 4x cube plus 3x squared by 6 plus 12x squared plus 6x by 36 and so on. Now the complete solution is just going to be this particular integral solution plus complementary function. And always remember why the particular solution comes. It is always generated out of whenever the differential equation is equal to some factor. That is, here the factor is 4x cube plus 3x squared. If that is 0, then we will never have a particular integral. When that is not 0, finding the particular integral is going to be the biggest part of the problem.
So students, we have come to the last. Let us summarize what we have learned in this module. We have learned that differential equations can actually help us understand a few things that we are interested in observing from a system, such as temperature and velocity, acceleration, and it can model a complex system, and it is different than a ordinary partial differential equation is different than a ordinary differential equations. We have understood what are independent variables, what are dependent variables, and how we can understand what is the order of the equation, what is the degree of ordinary differential equation, then how we can go about solving those equations numerically. Then in the next module we will see how we can handle partial differential equation. Thank you.